Weak bases are those that don't fully dissociate in water. Some examples are amines such as ammonia or trimethylammonia, pyridine, ammonium hydroxide, water, or any conjugate base of a weak acid. For example, acetic acid is a weak acid, and so this acetate ion here is an example of a weak base. If you were asked for the pH of a 3 molar solution of acetate ion and you were given the Ka of acetic acid of 1.77 times 10 to the negative 5, then the first thing we need to do is recognize that CH3COO- is an example of a weak base. So when it says a solution, we assume this is a solution in water, so we write out our equation, which is that we take our acetate anion and we put it in water. And this is going to undergo an acid-base reaction, which means that one hydrogen is going to be exchanged. So we're going to take one of these hydrogens and add it here. So we're going to get acetic acid, CH3COOH, and our water less one hydrogen, which gives us hydroxide, which is what we'd expect since we put a base in water, so we expect to get hydroxide out. So now we need to complete our Rice table. So reaction, initial, change, and equilibrium. Here we don't have any change in volume, so I can simply use the concentration that's given as my initial. So here we have 3.0 molar as our initial concentration of the acetate anion. The change is going to be just a little bit, because only a little bit's going to react because it's a weak base. So we can say minus x, which of course means we need to put plus x and plus x over here because anything we lose on the left is added to the right. We start with 0 of both of these, so the equilibrium is 3.0 minus x, x, and x. Now we need to use the equation Kb is equal to the concentration of CH3COOH times the concentration of hydroxide divided by the concentration of our conjugate base. But we weren't given Kb in our question. What we were given is Ka. So what we need to use is that Kw is equal to Ka times Kb for a conjugate acid-base pair. We're given Ka for the conjugate acid. What we need is Kb for our conjugate base. And we know Kw since that's just a constant at room temperature, which is 10 to the negative 14. So Kb is equal to 10 to the negative 14 over Ka. And we have our Ka given to us in our question up here. So this is equal to 10 to the negative 14 over Ka. Now we can fill in the values from the equilibrium row in our Rice table. So this is simply equal to x squared over 3.0 minus x, and we assume that x is small, so that 3.0 minus x is approximately equal to 3.0. This greatly simplifies our math. So this is still equal to 10 to the negative 14 over our Ka. So this is now x squared over 3 is equal to 10 to the negative 14 over Ka. Solving for x, we have that x is equal to the square root of 3 times 10 to the negative 14 over our Ka. So Ka to the minus 1. Plugging in our Ka here. So this is equal to 1.30 times 10 to the negative 4. And from above we see that x is equal to our concentration of hydroxide ion. So our POH is equal to negative log of x, which is equal to negative log of 1.3 times 10 to the negative 4. And that is 3.89. The question asked for the pH, which is equal to 14 minus the POH. So that's equal to 14 minus 3.89, which is 10.11. So our pH in this case is 10.11.